Modern gold extraction requires moving mountains of rock to yield handfuls of metal. To bridge that gap, the industry relies on a chemical shortcut, a solvent capable of aggressively stripping raw ore down to its pure gold core. For decades, the undisputed tool for this job has been sodium cyanide. It is the backbone of global wet metallurgy, used in thousands of facilities to leach gold from solid stone. But this efficiency comes with extreme biological risk. Sodium cyanide is highly volatile. Inhaling just 40 to 90 milligrams per cubic meter of its aerosolized dust induces severe respiratory distress. At higher concentrations, exposure becomes lethal in a matter of minutes. A patented chemical alternative called JIN CHAN claims to solve this. It is designed to replace sodium cyanide entirely, offering the exact same gold-dissolving power, but without the lethal toxicity. This presents a strict metallurgical paradox. The chemical aggression required to strip gold from stone and the chemical aggression that destroys human biology are supposed to be one and the same. How can a compound retain one property while completely discarding the other? This diagram shows the chemical formulas for both. On the left is the simple, linear structure of sodium cyanide. On the right is the branching formula for JIN CHAN. Notice that JIN CHAN also contains cyanide-like carbon-nitrogen groups, making its safety profile even more counterintuitive. JIN CHAN relies on re-engineering the behavior of its chemical bonds. By changing how the cyanide groups are anchored, the molecule reacts with gold while remaining completely inert in the presence of human tissue. Achieving environmentally safe gold extraction requires executing a molecular lockdown on a deadly chemical structure, preventing it from interacting with human biology while leaving it active for metallurgy. To understand how this lockdown works, we first have to look away from industrial minds and examine the microscopic engine of human respiration. This is a model of cytochrome oxidase A3, an enzyme critical to cellular respiration. Respiration is a continuous sequence of electron transfers, generating ATP. At the center is an iron ion, constantly cycling between an Fe2+ and Fe3+ state. In a normal cycle, these iron ions receive electrons and pass them directly to oxygen molecules. This activates the oxygen, allowing it to bond with hydrogen to form water and release a pulse of ATP energy. When sodium cyanide enters the body, it readily dissolves in water. This dissociation releases free cyanide ions, Cn-, into the bloodstream, which drift toward these cells. The specific danger lies on the carbon atom of that free cyanide ion. It possesses a highly reactive pair of long electrons. These electrons have a strong affinity for the empty orbitals of the Fe3+ iron ion inside the respiratory enzyme. They bind to the enzyme's active site, creating a stable, unwanted complex. Once bound, the iron is trapped in its Fe3+ state. The enzyme's catalytic function ceases. The iron can no longer accept or pass along any more electrons. The blood is still fully saturated with oxygen, but the cells are suffocating because the electron transfer chain has been severed. In biology, this mechanism is termed intracellular asphyxiation. Sodium cyanide's extreme toxicity depends entirely on one specific variable: the freedom of the cyanide ion to detach, roam, and bind with cellular iron. If the free cyanide ion is so dangerous, the logical step is to discard it entirely and use a different chemical to dissolve the gold. The problem is the elemental nature of gold itself. Solid gold is notoriously inert, easily resisting oxidation and attack from standard chemicals. To dissolve it, you must introduce a highly aggressive ligand, a molecule capable of forcefully gripping the gold atom and pulling it into a water-soluble complex. This diagram shows the exact leaching equation for sodium cyanide. In the presence of water and oxygen, the cyanide reacts directly with solid gold. Look at the resulting product. Two free cyanide ions surround and bind to a single central gold atom, pulling the previously solid metal into the liquid solution.
The mechanism relies on the exact same lone pair of electrons on the carbon atom. The chemical property that makes it a biological poison is precisely what makes it a perfect metallurgical tool. A viable replacement cannot abandon this chemical gripping ability. It must replicate it to dissolve gold, while physically blocking ions from interacting with human cells. This is where the engineering of JIN CHAN becomes critical. Its primary active ingredient is a chemical called carbonated melamine cyanurate. The structural difference begins with the bonds. sodium cyanide, relies on an ionic bond. This is a weak connection that easily snaps the moment it touches water, instantly setting the deadly cyanide ion free. JIN CHAN discards ionic bonds. Inside this massive molecule, the cyanide-like groups are attached via covalent bonds. These act like thick steel rebar, firmly locking the groups to the central molecular ring. Beyond just the strength of the bonds, the physical architecture of the molecule itself is large, branching, and exceptionally complex. This bulk creates a structural defense mechanism known as steric hindrance. The sheer physical size and density of the surrounding molecule acts as a permanent shield against outside interactions. Gold extraction requires an alkaline environment. Under these specific conditions, the steric hindrance completely prevents the molecule from degrading or breaking apart. It is physically unable to release free cyanide ions into the surrounding water or into a human bloodstream. The engineering of the JIN CHAN molecule creates a cage that prevents the active groups from ever reaching the sensitive respiratory enzymes in a human cell. If these cyanide groups are permanently locked down and shielded, the mechanical question is how they can possibly reach out and dissolve solid gold. The answer lies in the different scales of the targets. Steric hindrance blocks the molecule from entering the narrow active sites of human enzymes, but it does not stop the groups on its outer edges from reacting with the broad surface of gold ore. This diagram shows the JIN CHAN leaching equation. When it interacts with gold in the presence of oxygen and water, it forms an entirely new complex. Instead of sending out small, detached ions to retrieve the gold, the entire massive structure of the JIN CHAN molecule acts as a single unified ligand. The cyanide-like groups on the exterior coordinate with the gold, but the resulting gold JIN CHAN complex is massive. It is far too large to pass through the biological barriers that a free cyanide ion would easily cross. Working collaboratively with the other chemical components in the agent, it systematically oxidizes the gold and locks onto it. The agent yields the exact same macro-scale result, dissolving solid gold, but executes the process using a strictly caged micromechanism. Moving from theoretical chemistry to mass industrial production reveals real-world imperfections. This is why JIN CHAN is officially classified as a low-toxicity compound, rather than zero toxicity. During large-scale synthesis, unavoidable side reactions occur. These reactions can leave microscopic trace amounts of free cyanide in the final commercial product. To mitigate this, the chemical engineers designed a physical failsafe into the mixture itself. This is visible as a distinct black sludge that settles at the bottom of dissolved tanks. This water-insoluble matter makes up 3% or less of the product. It is not industrial waste. It consists predominantly of iron oxides. The addition is highly intentional. The iron oxide acts as a chemical anchor, providing further structural stability to the carbonated melamine cyanurate. By forcing the molecule to remain intact under normal industrial conditions, this residue acts as a built-in safety net against chemical degradation. This chemical formulation succeeds because it bridges theoretical chemistry with pragmatic engineering. By combining covalent locks with chemical stabilizers, the industry has managed to diffuse one of its most dangerous tools without blunting its edge.